Hello, and in this second short video, I'm going to be looking at AC power in resistors. Now, the thing about resistors is that the current flowing through them is always proportional to the voltage across them. That's what Ohm's law tells us. The current is the voltage divided by the resistance. So, if we were to plot the voltage across a resistor and the current through a resistor, when the voltage is sinusoidal, we would get curves like this. A sinusoidal voltage here, a sinusoidal current, which is always proportional to the voltage. So when the voltage is negative, the current is negative. When the voltage is positive, the current is positive as well. And if we multiply the voltage and the current together, that will give us the instantaneous power, the power being dissipated in the resistor at any instant in time. And if we plot that, just the voltage times the current, we end up with a curve like this purple one, the power. You'll notice that it's oscillating at twice the frequency that the voltage and the current are oscillating at. And that's a direct result of a simple trigonometrical identity. You'll also notice that the power is always positive. The power dissipated by a resistor is always positive. Resistors cannot store energy, they cannot input energy back into the circuit, so they're always taking energy out of the circuit. That means a positive power being dissipated. Now, what is that power? Well, if we let the voltage across our resistor be V0 cos omega t, then the current through the resistor is going to be, by Ohm's law, I0 cosine omega t. It'll be in phase with the voltage, which is just V0 cosine omega t divided by R, the resistance of the resistor. And the amplitude of the current, I0, is just the amplitude of the voltage divided by the resistance R. So the power, instantaneous power, being lost by the resistor is V0 cosine omega t times I0 cosine omega t, or V0 I0 cosine squared omega t. And here we can use a standard trigonometrical identity to write cosine squared of an angle in terms of a constant plus cosine of twice that angle. Here, the standard trigonometrical identity we need is the one that says cosine squared x equals a half plus cosine 2x divided by 2. Apply that. That gives us our instantaneous power is the magnitude of the voltage times the magnitude of the current divided by 2 plus the magnitude of the voltage times the magnitude of the current divided by 2 times cosine 2 omega t. And that's an oscillation which is going at twice the frequency that the current and the voltage are going at. Now, quite often we don't want to know what the instantaneous power is in the resistor. What we're interested in is the average power in the resistor, because it's the average power that, when multiplied by time, gives us the total energy that's been dissipated in the resistor, and that tells us how hot the resistor is going to get. So, what can this formula tell us about the average value of the power? Well, the average value of the power will be the average value of this term plus the average value of this term. But the average value of this term is 0, because it's a cosine wave. It oscillates up and down around 0. So that's going to give me an average value of 0, which means that the average value of the power being dissipated in my resistor is the amplitude of the voltage across it times the amplitude of the current flowing through it divided by 2. And since V0 and I0 are constants, I could just write it like this. I could now apply those formulas that I derived from Ohm's law, that the magnitude of the current is equal to the magnitude of the voltage divided by the resistance, and express this in two other forms as V0 squared over 2R, or also I0 squared times R over 2, where again I've just expressed the average power in terms of the amplitude. That's the 0 to peak amplitude of the voltage and the resistance, or the 0 to peak amplitude of the current and the resistance. What about phasors? Usually when we're dealing with AC circuits, we represent the voltages and the currents in the circuit in terms of a phasor representation, rather than a amplitude or a time-dependent function. Can we express the average power dissipated in this resistor in terms of the phasor representation of the voltage across the resistor, or the phasor representation of the current flowing through the resistor? And the answer is yes. And it's actually quite straightforward, because the magnitude of the phasor representation of the voltage is just equal to the 0 to peak voltage, and the magnitude of the current phasor is just equal to the 0 to peak amplitude of the current. So I could just directly substitute in for V0 and I0 in terms of the magnitude of the phasor representations, and that would give me that the average power dissipated by this resistor is the magnitude of the phasor representation of the voltage across it squared divided by 2R, which is also equal to the magnitude of the current phasor squared times R over 2. And those are the only formulas that we need for representing the power dissipated by a resistor, on average, in terms of the phasor representations of the voltage and the current. Next time, we'll go and have a look at AC power in capacitors and inductors.